March 14, 1941, 07, for 2 hours. RAF Kenley, Surrey, England. Squadron leader Geoffrey Davies climbed into his Hurricane's cockpit for what might be his last mission. He didn't know that 50 feet away, a 32-year-old woman named Beatrice Shilling was about to commit what could be considered treason, installing an unauthorized modification on his fighter that violated 40 different RAF regulations. If it failed and Davies died, Shilling would face court-martial, imprisonment, and the end of her career. But if it worked, she would save 2,100 British pilots and hand the Royal Air Force the one thing they desperately needed: an engine that didn't cut out at the exact moment. German fighters attacked. For 11 months, the Luftwaffe had exploited a fatal flaw in every Spitfire and Hurricane: push into a dive to attack, and the Rolls-Royce Merlin engine died for 1.5 seconds. 1.5 seconds, enough time for a Messerschmitt Bf 109 to close 300 yards and put bullets through a stalled British fighter. 14 Hurricanes shot down in 1 week, 9 all because of carburetor physics that British plus engineering couldn't solve. Rolls-Royce said they needed 2 years to fix it. The RAF didn't have 2 months. Pilots were dying every day, killed not by superior German tactics or better aircraft, but by their own engines betraying them at 15,000 feet. Beatrice Shilling's solution: a brass washer the size of a 50-cent piece, with a hole precisely 0.04 inches in diameter, 50 cents worth of metal, 60 seconds to install, and it would transform the Battle of Britain more decisively than any tactical innovation, any strategic bombing campaign, any intelligence breakthrough. This is the story of how one woman's unauthorized modification became the most important 50 cents Britain ever spent, and why German pilots stopped celebrating when British fighters dove to attack, because Miss Shilling's orifice had just turned their prey into predators. Part 1. The woman engineers didn't want. November 1939. Royal Aircraft Establishment, Farnborough. Beatrice Shilling walked through the gates of the Royal Aircraft Establishment on her first day, knowing that most of the men she'd be working with didn't believe women belonged in engineering. Some wouldn't speak to her directly. Others would dismiss her technical opinions. A few would assume she was someone's secretary. She didn't care what they believed. She cared about engines. Shilling had grown up taking apart motorcycles. At 14, she'd bought her first Norton with money saved from odd jobs. She'd stripped a 2-stroke engine down to individual components, learned how every part functioned, memorized the relationship between compression ratios and power output, then rebuilt it herself. No manual, no instructor, just mechanical intuition and relentless curiosity. She'd raced that Norton at Brooklyn's 106 miles per hour average speed, fast enough to earn the British Motorcycle Racing Club Gold Star. Only 3 women in history had earned that award. Shilling was the second. The men who'd watched her race came away respecting her, but racing was considered eccentric. Engineering was serious work reserved for serious men. The Royal Aircraft Establishment was Britain's primary aeronautical research facility. 800 engineers, scientists, and technicians working on aircraft design, engine development, weapons testing, and aerodynamic research. Of those 800 personnel, exactly 2 were women. One was a secretary. The other was Beatrice Shilling, appointed principal technical officer in charge of carburetor research and development. The appointment had caused controversy. Several senior engineers had protested to management. A woman couldn't possibly understand the complex thermodynamics of fuel delivery systems under combat conditions. How could she relate to what pilots experienced? She'd never flown a fighter. She'd never been in combat. She was a motorcycle enthusiast, not a serious aeronautical engineer. Shilling's supervisor, RF Harker, had defended the appointment with one sentence: "She understands carburetors better than anyone in Britain, including all of you." He was right. Shilling had spent years studying fuel delivery systems, not in textbooks, but in engines screaming at 10,000 RPM on racetracks. She'd learned how engines failed under extreme stress, high G-turns, sudden acceleration, severe lean angles. She could diagnose problems from sound, from vibration, from the subtle changes in engine behavior that instruments couldn't detect. That intuitive understanding would prove more valuable than any doctorate when British fighters started dying from an engineering problem that traditional analysis couldn't solve. Part 2. The problem that was killing Britain. 1940. The Battle of Britain begins. The Royal Air Force had switched to 100-octane fuel. Higher octane allowed more boost pressure without predet. More boost meant 1,310 horsepower from the Rolls-Royce Merlin engine instead of 1,100. The Spitfire Mark II could hit 370 miles per hour in level flight fast enough to catch Messerschmitt Bf-19s that had previously been too fast to intercept, but the increased power came with a fatal flaw. The Merlin engine used a Skinner's Union carburetor flow chamber design that relied on gravity to maintain proper fuel level. Under normal flight conditions, it worked perfectly. Under negative G conditions, the sudden dive that characterized every aerial attack failed catastrophically. The physics was simple and brutal. When a Spitfire or Hurricane pushed into a sudden dive, the negative G force threw fuel to the top of the float chamber. The jet that fed fuel to the engine was at the bottom of the chamber. For 1.5 seconds, the engine received too much fuel, flooding the carburetor and killing combustion. The Merlin engine simply stopped. 1.5 seconds doesn't sound like much. In combat at 300 miles per hour, 1.5 seconds meant the attacking British fighter lost 660 feet of altitude, while the pilot fought to restart the engine. The German pilot had time to recognize the stall, break off his own evasive maneuver, and reverse the engagement. The British pilot, temporarily helpless, became the target instead of the attacker. German pilots recognized the weakness and exploited it ruthlessly. Messerschmitt Bf-109 pilots learned to watch for the telltale signs of a British fighter entering a dividend. Then they'd deliberately bait the attack, knowing the Spitfire or Hurricane's engine would die. The instant the British engine coughed and failed, the German pilot would reverse course and attack the now helpless fighter. The combat reports told the story with terrible clarity. July 15, 1940, Flight Lieutenant James Cox engaged Bf-109 at 16,000 feet, entered diving attack. Engine cut out. Cox attempted restart while diving. Engine restarted at 12,000 feet. Bf-109 had circled back and was firing from 200 yards. Cox took hits to fuselage and port wing. Crash landed at Biggin Hill. Aircraft total loss. July 23, 1940. Pilot Officer David Reynolds spotted two Bf-109s at 14,000 feet. Dove 2, intercept. Engine failure during dive. Unable to restart for 2.8 seconds. Pilot estimate. Aircraft continued diving under gravity. Reynolds regained engine power at 9,000 feet. Both Bf-109s had escaped. Reynolds returned to base. August 4, 1940. Squadron leader Robert Thompson engaged Bf-109 over Dover. Entered steep dive from 18,000 feet. Engine cut out. Bf-109 pilot recognized engine failure and reversed engagement. Thompson took cannon fire while attempting engine restart. Aircraft hit in engine cowling and cockpit. Thompson killed. Aircraft crashed into channel. The pattern repeated across every squadron. British pilot spots German fighter. British pilot enters diving attack. Engine dies. German fighter survives or worse. Kills the British pilot while his engine is dead. Fighter command tracked the statistics meticulously. August 1942, 127 combat engagements involving diving attacks, 73 reported engine failures, 57.5%, 29 British fighters lost while engines were temporarily failed, 19. German fighters escaped attacks due to British engine failures. The numbers were unsustainable. RAF Fighter Command was losing experienced pilots faster than training schools could replace them. Every Hurricane and Spitfire pilot knew about the carburetor problem. Many pilots hesitated to commit to diving attacks, reducing their combat effectiveness. Some pilots died despite knowing about the flaw because, in the chaos of high-speed combat, training and instinct took over. An instinct said dive on the enemy. Their engines killed them before the Germans got the chance. Part 3. The engineering establishment says wait 2 years. September 1940, Rolls-Royce Derby. Rolls-Royce engineers had known about the carburetor problem since July. They'd been working on a solution, a pressure carburetor that would eliminate the float chamber entirely. Direct fuel injection under pressure, similar to the system used in German Daimler-Benz engines. No float chamber meant no flooding. The Merlin engine would maintain perfect fuel delivery, regardless of aircraft attitude or G-forces. It was the proper engineering. Solution complete redesign of the fuel delivery system. Extensive testing under all conceivable conditions. careful integration with existing engine management systems. Proper engineering took time. Rolls-Royce estimated the pressure carburetor would be ready for production testing in late 1942, with full production beginning in 1943, maybe 1944, if unexpected problems emerged during testing. The Air Ministry received this timeline and did the casualty calculations. Current pilot loss rate approximately 40 pilots per month dying, partially or entirely due to engine failures. During combat maneuvers, projected timeline to pressure carburetor deployment, 24 to 36 months. Total pilot deaths, if engine problems continued, 960 to 1,440 pilots. The mathematics were unacceptable. Britain didn't have 960 pilots to sacrifice while waiting for proper engineering solutions. Fighter command was already stretched thin. Every experienced pilot lost made the remaining pilots more vulnerable. The downward spiral had to be stopped immediately. The Air Ministry contacted the Royal Aircraft Establishment. Find a stopgap solution, something that works now, not in 2 years. It doesn't have to be perfect. It just has to keep pilots alive until the pressure carburetor is ready. The problem landed on Beatrice Shilling's desk in October 1940. She'd been reading the combat reports for months. She'd interviewed pilots who'd survived engine failures. She'd studied the Skinner's Union carburetor design, understood its strengths and weaknesses, recognized why it failed under negative G loads. The float chamber flooded because fuel could flow unrestricted when gravity reversed. Simple physics. What if you restricted the flow? Not completely. The engine still needed fuel. But what if you limited maximum fuel flow to slightly less than what the engine demanded at full throttle? The carburetor couldn't flood if fuel couldn't surge into the float chamber faster than the engine consumed it. The solution was almost absurdly simple. A brass disc with a precisely calculated hole in the center. Install it in the fuel line before the carburetor. Maximum fuel flow would be limited by the size of the hole. Make the hole the right size, and you'd prevent flooding without starving the engine. Shilling machined the first restrictor herself in the Ray workshop, a small brass component, thimble-shaped, 0.125 inches in diameter. The hole in the center was 0.04 inches. Those dimensions were critical. Too large and the carburetor would still flood. Too small and the engine would starve at full power. She tested 17 different sizes on a bench engine before finding the right one. Then she simplified the design. A flat washer was easier to manufacture than a thimble, easier to install, easier to replace if damaged. The final design looked like something you'd buy at a hardware store for 50 cents. It worked perfectly in bench tests. The restrictor prevented flooding during simulated negative G conditions, while maintaining adequate fuel flow for full power operation. But bench tests weren't combat. Bench tests were controlled conditions in a laboratory. Combat was 300 miles per hour at 15,000 feet with Messerschmitt BF-19s shooting at you. She needed to test it on an actual aircraft. Under actual combat conditions, the problem was getting permission. Part 4. Breaking every rule to save lives. March 14, 1941. RAF Kenley. Installing unauthorized modifications on RAF fighters. Violated approximately 40 different regulations. The rules existed for good reasons. Some controlled experimentation could introduce dangerous failures, kill pilots, destroy valuable aircraft. Every modification required extensive testing, documentation, approval from multiple levels of command, and systematic implementation through proper channels. Following those procedures would take months. Pilots were dying now. Beatrice Shilling decided to skip permission and ask forgiveness later. She loaded 6 restrictors into her leather satchel, climbed on her Norton motorcycle, and rode to RAF Kenley, one of Fighter Command's busiest stations. Home to 4 squadrons flying constant combat patrols over the Channel, she found Sergeant William Cooper in the maintenance hangar. Cooper had worked on Merlin engines for 3 years. He'd seen 19 pilots die from engine failures. When Shilling showed him the brass washer and explained what it did, he didn't ask about authorization forms or testing documentation. He just nodded and reached for his TOOLKIT. Squadron leader Geoffrey Davies Hurricane sat on the dispersal pad. Engine warming up. 20 minutes until takeoff for combat patrol over Dungeness. Cooper worked fast. He disconnected the fuel line between the pump and carburetor. The restrictor slid into place, a brass washer the size of a large coin. He welded it with a small butane torch. 60 seconds of work. The modification was invisible unless you knew where to look. Davies would fly with the restrictor. He didn't know it was there. Shilling hadn't told him, hadn't told the squadron commander, hadn't told anyone except Cooper. If the restrictor failed and Davies died, there would be no paper trail, no authorization forms, no testing documentation, just a dead pilot and a brass washer that shouldn't have been there. Shilling would face court-martial imprisonment, and the knowledge that her unauthorized modification had killed a man. She watched Davies's Hurricane take off. The Merlin engine roared smoothly. Davies climbed to 15,000 feet and turned south toward the Channel, toward the German fighters that had been active over Dungeness all week. Shilling waited on the tarmac with her binoculars. Cooper stood beside her. Neither spoke. 40 minutes passed. An hour. Radio silence from Davies's patrol section. That could mean anything: no contact with enemy fighters, or contact so intense there was no time to report. Or Davies was dead, and his Hurricane was scattered across a French field. At 0937 hours, the radio crackled. 3 Hurricanes inbound. 2 minutes out. All 3 aircraft returning. No losses. Davies landed first. He taxied to dispersal, cut the engine, climbed out of the cockpit. He was smiling. That was unusual. Pilots didn't usually smile after combat patrols. They looked exhausted, haunted, drained. Davies looked excited. Cooper asked the critical question. "Any problems with the engine, sir?" Davies looked at Cooper, then at Shilling, then back at Cooper. "Best the Merlin's ever run," he said. Dove on to Messerschmitts over engine never missed a beat. Part 5. The perfect dive. Davies described the engagement in detail. He'd spotted to be F-109s at 14,000 feet, both aircraft flying east toward France. Davies had positioned his section above the altitude advantage, the fundamental principle of fighter combat. He'd pushed into a steep dive, 400 miles per hour, negative G forces strong enough to lift him against his harness straps. The dive that should have killed his engine. The Merlin kept running, full power through the entire dive. No cough, no stumble. Number 1.5-second death that had killed so many of his squadron mates. Davies had closed to 200 yards before the German pilots saw him. He'd fired a 3-second burst from his 8.303 machine guns. Saw strikes on the Bf-109's left-wing root and fuselage. The German fighter broke hard right and fled toward France at full throttle. Davies had pulled up, climbed back to altitude, and resumed patrol. The engine had performed flawlessly. It was the first time in 11 months that Davies had successfully pressed a diving attack without his engine cutting out. It was the first time he'd attacked a Bf-109 without wondering if his own engine would kill him before the German pilot did. He wanted to know what maintenance had done to his Hurricane. What had changed? What was different? Shilling explained. The restrictor, the brass washer, the fuel flow limitation, a 50-cent piece of metal that prevented carburetor flooding during negative G maneuvers. Davies stared at her for 5 seconds. Then he turned to Cooper and said 7 words that would change the Battle of Britain. "Put that thing in every Hurricane on this station." Today, Shilling explained it wasn't authorized. The modification violated regulations. She could be court-martialed for installing it without proper approval. Davies didn't care about regulations. He cared about surviving combat. Every pilot at Kenley had lost friends to engine failures. 19 pilots dead in 6 months because their engines betrayed them at the worst possible moment. Davies said if the Brask wanted to court-martial him for installing an unauthorized modification, they could do it after the war. Right now, his squadron needed working engines. Cooper installed restrictors in 4 more Hurricanes that afternoon. Shilling had brought 6 total. She kept one for continued testing. 5 Hurricanes flew combat patrols with restrictors over the next 3 days. 0 engine failures. 12 diving attacks successfully pressed against German fighters. Pilots reported the Merlin engines ran perfectly, better than perfectly. Some claimed they were getting more power at altitude. Word spread with the speed of combat urgency. By March 18th, every squadron commander in 11 Group knew about the restrictor. They wanted it, all of them, immediately. Shilling received 14 phone calls in 2 days. Could she come to their stations? Could she bring more? How fast could they be manufactured? How quickly could installation begin? Part 6. The Air Ministry finally pays attention. The official approval came faster than anyone expected. For days after Davies's successful combat test, the Air Ministry found Shilling's proposal through every bureaucratic layer that normally would have taken months to navigate. They called it a war-winning modification. Rolls-Royce received the production contract. They could manufacture 500 restrictors per week, simple brass washers, precisely machined, each one identical to the prototype Shilling had made in the Ray workshop. Installation would begin immediately at every fighter station in Britain. The restrictor could be fitted without removing aircraft from service, critical because Fighter Command couldn't afford to ground squadrons. German fighters still crossed the Channel daily. Every Hurricane and Spitfire needed to stay operational. Shilling assembled a small installation team, 3 engineers from Farnborough to civilian mechanics. They would tour RAF stations across Britain, supervising installation and training ground crews. By March 25th, installation teams were ready. 600 restrictors manufactured, 40 stations scheduled, 3,000 Merlin engines waiting for the modification that would save their pilots' lives. Shilling started her Norton motorcycle and headed north to Biggin, Hiltha, busiest fighter station in 11 Group, 32 Spitfires, 21 Hurricane, 4 squadrons rotating through continuous combat operations. Station Commander Group Captain Grace met her at the gate. He'd lost 7 pilots to engine failures in the past 2 months. He wanted restrictors installed immediately, a day if possible. Ground crews worked in shifts, for aircraft at a time. Each installation took 12 minutes. Disconnect fuel line between pump and carburetor, weld restrictor in place, using precise technique. Fuel line test for leaks, mark aircraft log with installation, date and technician signature. The welding had to be perfect. A faulty weld at altitude could starve the engine completely, creating the exact problem the restrictor was meant to solve. Shilling supervised every installation personally. She checked every weld, tested every connection, rejected 3 restrictors that didn't meet specifications. Pilots watched the modifications with intense interest. Flight Lieutenant James Lacey had 41 combat missions under his belt. He'd experienced engine failure twice, both during critical moments in dogfights. He asked Shilling how a simple washer could solve such a complex carburetor problem. She explained fuel flow physics, float chamber dynamics, negative G effects on liquid fuel. The restrictor limited maximum fuel flow to slightly less than full power demand. The carburetor couldn't flood if fuel couldn't surge into the float chamber faster than the engine consumed it. Lacey understood immediately. He was an engineering graduate from Cambridge. He called it brilliant simplicity. By March 28th, all 53 Merlin engines at Biggin Hill had restrictors installed. Shilling moved to Hornchurch, then Northolt, then Tangmere. The pattern repeated at every station. Ground crews working 12-hour shifts. Pilots flying combat patrols with modified engines. 0 failures reported. The restrictor worked exactly as designed. Part 7. The nickname that became legend. Pilots started calling it Miss Shilling's Orifice. The nickname came from Sir Stanley Hooker, chief engineer at Rolls-Royce's Supercharger division. It was crude British humour, slightly inappropriate, deliberately provocative. Hooker thought it was hilarious. Some of the more conservative Air Ministry officials thought it was scandalous, referring to a critical engine modification with what was essentially a sexual innuendo. Shilling didn't mind. She'd spent 6 years working with RAF personnel. She understood how military men dealt with stress, how humour helped them process the constant proximity to death. If crude nicknames helped them remember the modification, she'd accept any name they wanted to use. The nickname spread faster than the restrictor itself. By April, every pilot in Fighter Command knew about Miss Shilling's Orifice. They requested it specifically by that name. Squadron commanders wrote official requests. Request immediate installation of Miss Shilling's Orifice on all operational aircraft. Some pilots refused to fly combat missions until their aircraft had the modification installed. Squadron commanders supported them. They'd seen too many good pilots die from preventable engine failures. They weren't going to send men into combat with faulty equipment. When a simple fix existed, the German Luftwaffe noticed the change quickly. Intelligence reports from early April mentioned improved RAF fighter performance during diving attacks. British fighters no longer broke off pursuit during negative G maneuvers. Messerschmitt pilots could no longer exploit the carburetor weakness. The tactical advantage had disappeared. German fighter pilots, who'd learned to bait British aircraft into diving attacks, found themselves suddenly vulnerable. The British fighters that dove on them didn't stall anymore. The hunters had become the hunted. Part 8. The numbers tell the story. Fighter Command tracked combat statistics meticulously. Every engagement, every kill, every loss was documented, analyzed, and compiled into reports that revealed patterns invisible to individual pilots, but clear from statistical analysis. March 1941, before the restrictor, RAF fighters reported engine failures in 38% of diving attacks against German aircraft. 47 Hurricanes and Spitfires lost in combat. 61 German aircraft destroyed. Kill-to-loss ratio 1.3 to 1, barely breaking even. April 1941. After the restrictor, engine failures during diving attacks dropped to 0.4%. 29 British fighters lost in combat. 94 German aircraft destroyed. Kill-to-loss ratio 3.2 to 1. The improvement was dramatic and immediate. The restrictor wasn't the only factor. Pilot experience, tactical improvements, and better coordination all contributed, but squadron commanders credited the restrictor as a major contributor to the improved performance. Pilots reported increased confidence in combat. Flight Lieutenant Robert Stanford Tuck flew Spitfires out of duck. He'd experienced engine failure 4 times before the restrictor. After installation, he pressed diving attacks without hesitation, without that split-second mental calculation of whether his engine would fail at the critical moment. He destroyed 3 Bf-109s in May, 2 more in June. He credited the restrictor with giving him the confidence to commit fully to aggressive tactics instead of holding back, always wondering if his own engine would betray him. The psychological effect was as important as the technical fix. Pilots flew differently when they trusted their engines. They took calculated risks they'd avoided before. They pressed attacks they'd previously broken off. They fought with the aggression that had been suppressed by 11 months of watching engines fail at the worst possible moments. Part 9. Beyond Fighter Commander. Success in Fighter Command spread the restrictor throughout the RAF. Coastal Command requested them for their Beaufighters hunting U-boats over the Atlantic. Bomber Command wanted them for training aircraft. The Fleet Air Arm inquired about installation on carrier-based fighters. Shilling coordinated production expansion with Rolls-Royce. By June 1941, they were manufacturing 1,000 restrictors per week, double the initial production rate. The demand exceeded supply. Stations were prioritized based on combat intensity. Frontline fighter squadrons first, then training units, then reserve aircraft. By mid-April 1941, Shilling's installation team had fitted restrictors to 2,100 Merlin engines. Every Hurricane and Spitfire in Fighter Command, every operational training unit, every aircraft in reserve status awaiting deployment. The modification became standard equipment. New aircraft rolling off production lines at Castle Bromwich and Southampton came with restrictors pre-installed. Quality control inspectors checked them as carefully as they checked propeller installation or gun harmonization. The pressure carburetor was still in development. Rolls-Royce estimated it would be ready for production in 1943, but the restrictor worked so well that some engineers questioned whether the pressure carburetor was even necessary. Why redesign the entire fuel system when a 50-cent brass washer solved the problem? Shilling knew the answer. The restrictor was a stopgap, brilliant, effective, life-saving, but temporary. It limited fuel flow slightly, which meant slight power reduction at absolute maximum throttle. The difference was negligible in combat conditions, but it existed. The pressure carburetor would eliminate the negative G problem completely, with no power limitations. Full engine performance under any flight condition. That was the proper engineering solution. But until 1943, Miss Shilling's orifice kept RAF pilots alive, and that was enough. Part 10. The German Perspective. Luftwaffe. Intelligence struggled to understand what had changed. British fighter performance had improved dramatically in April 1941. The improvement wasn't gradual, it was sudden and universal across all RAF squadrons. German fighter pilots reported that RAF aircraft no longer experienced engine failures during diving attacks. This suggested either complete engine replacement across the entire RAF fighter force. Impossible. Such replacements would take months and require grounding squadrons. New fuel formulation that prevented carburetor flooding. German chemists analyzed captured British aviation fuel and found no changes. some modification to existing engines that German intelligence couldn't identify. German intelligence couldn't discover was that the entire change came from a brass washer, the size of a coin, installed in 60 seconds, invisible unless you knew where to look. Messerschmitt, Bf 109 pilots, who had previously enjoyed significant tactical advantages, found themselves suddenly on equal footing. The engine stalls they'd learned to exploit had vanished. British fighters dove with full confidence, pressed attacks aggressively, and no longer broke off pursuit at critical moments. German tactical doctrine had to adapt. Fighter pilots who'd learned to bait British aircraft into diving attacks abandoned those tactics. They no longer worked. The engagement pattern changed fundamentally. One Luftwaffe pilot, Oberleutnant Werner Mulder Zayes, reported in his after-action assessment from May 1941, English fighters now pressed diving attacks with confidence previously absent. Previous tactical advantage during vertical maneuvers appears eliminated. Unknown modification suspected. He was right about the modification. He never learned it was a brass washer. Part 11. The recognition that came slowly. Beatrice Shilling's contribution wasn't publicly acknowledged during the war. Military secrecy prevented discussion of technical modifications that gave tactical advantages. The restrictor remained classified not because it was sophisticated technology, but because acknowledging its existence might alert German intelligence to the specific vulnerability it addressed. Pilots knew about Miss Shilling's orifice, ground crews knew, squadron commanders knew, but the public didn't learn about it until after the war ended. In 1946, the Air Ministry declassified technical documents related to Merlin engine modifications. The restrictor was mentioned briefly, a simple device that prevented carburetor flooding during negative G maneuvers. The dry technical language didn't capture the human impact. 2,100 engines modified, countless pilots saved, the Battle of Britain influenced by 50 cents worth of brass. Shilling continued working at the Royal Aircraft Establishment. She never sought publicity for the restrictor. She considered it one project among many important, certainly, but not necessarily more significant than her other work on cold weather starting systems, high-altitude performance, or supercharger efficiency. In 1948, King George VI appointed her Officer of the Order of the British Empire. The ceremony took place at Buckingham Palace. Shilling wore formal dress, accepted the medal, posed for photographs, then went back to work at Farnborough the next morning. She never stopped engineering, never stopped solving problems, never stopped proving through quiet competence that women belonged in technical fields. Part 12. The pressure carburetor. Arrives. Rolls-Royce finally introduced the pressure carburetor in January 1943, 2 years after Shilling's restrictor began saving pilots' lives. The new carburetor eliminated the negative G problem completely using fuel injection. Principles similar to German Daimler-Benz engines. No float chamber, no flooding, perfect fuel delivery under any flight attitude of G-loading. But converting existing aircraft to pressure carburetors required extensive modifications. Remove the old carburetor, install new fuel pumps, rewire engine controls, test systems integration. Each conversion took 8 hours of skilled labor. During those 8 hours, the aircraft couldn't fly combat missions. Fighter Command couldn't afford to ground squadrons for extended maintenance. The air war over Europe was intensifying. Every squadron needed maximum operational availability, so they kept the restrictors. Many aircraft flew with Miss Shilling's orifice until 1944, until the end of the war. In 1945, new production Spitfires and Hurricanes received pressure carburetors, but older aircraft kept their restrictors. Pilots trusted them. Ground crews knew how to maintain them. If it worked, why change it? The restrictor that was supposed to be a temporary stopgap became a permanent feature on thousands of aircraft for 4 years of war. It was never replaced on many engines simply because there was no need. The brass washer did its job perfectly until those engines were retired from service. Part 13. Beyond the restrictor, Shilling's work didn't stop with the famous brass washer. The Royal Aircraft Establishment had dozens of critical problems requiring immediate solutions. Cold weather modifications. 1941-1942. Spitfires deployed to Russia faced Arctic conditions that British engines weren't designed for. Temperatures dropped to -40 degrees Fahrenheit. Standard engine oil turned to sludge. Batteries died. Fuel lines froze. British pilots couldn't start their aircraft. Shilling developed cold start procedures using preheated oil and modified fuel mixtures. She worked with Soviet ground crews who had no experience with Merlin engines, creating maintenance procedures simple enough to implement with basic tools in sub-zero conditions. It worked. Spitfires flew combat missions over Murmansk through the winter of 1941-1942, supporting Soviet forces against German attacks. High-altitude performance, 1942-1943. Spitfire variants flew at 35,000 feet altitudes, where the Merlin engine struggled. Thin air, low oxygen content, fuel mixture requirements became critical. Too rich, and the engine flooded. Too lean, and it overheated. Shilling developed altitude compensating carburetor modifications that improved power output by 8% above 30,000 feet. The improvements seemed small, but at extreme altitudes, where engines operated at performance limits, 8% meant the difference between catching German reconnaissance aircraft or watching them escape. Wet. Runway braking 1950s. By the 1950s, jet aircraft had replaced piston fighters. But landing accidents killed more pilots than engine failures. Understanding how water on runways affected tire friction could save lives, Shilling researched the physics of wet runway braking, published 3 technical papers on the subject, and influenced runway design standards that remained in use for decades. The Bobsled Project, 1956, perhaps her strangest assignment, designing a bobsled for the Royal Air Force Olympic team, an eccentric project for an aeronautical engineer. But bobsled design involved aerodynamics, weight distribution, and friction management skills Shilling had mastered over 30 years. The RAF team used her bobsled design in competition. They didn't win medals, but they didn't crash either. For Shilling, that counted as success. Part 14. The private life behind the engineer. Shilling married George Naylor in September 1938. He worked at the Royal Aircraft Establishment as an aerodynamicist. They'd met through work, bonded over shared love of engineering and motorcycles. When war started, Naylor volunteered for RAF Bomber Command. He flew Avro Lancasters with 625 Squadron 31 combat missions over Germany. He earned the Distinguished Flying Cross for completing extra tours beyond his required service. Shilling worried about him every time he flew. She understood bomber loss rates better than most civilians. Bomber Command suffered higher casualties than any other RAF branch. Statistical analysis showed that 1 in 2 bomber crew members didn't survive the war. Naylor beat those odds. He survived his tours, returned to Farnborough in 1944, and resumed aerodynamics research. They never talked about his missions. He never asked about her projects. They kept work and marriage in separate compartments, a common coping mechanism for couples, where both partners dealt with classified wartime work. Shilling continued racing motorcycles when time permitted. She'd stopped competing at Brooklands when war started. The famous circuit had been converted to aircraft production facilities, but she still rode her Norton. Fast riding helped her think, solve problems that laboratory work couldn't crack. Some of her best engineering ideas came while riding at 90 miles per hour on country roads, the restrictor included. The insight about fuel flow limitation had occurred during a ride through Surrey in December 1940. When she'd suddenly understood that preventing flooding was simpler than redesigning the entire carburetor. Part 15. The glass ceiling that never broke. Beatrice Shilling worked at the Royal Aircraft Establishment for 33 years from 1939 to 1969. She never reached the top. Administrative positions. Those roles were reserved for men, regardless of accomplishment or expertise. The RAF leadership structure didn't promote women to director-level posts. This wasn't officially acknowledged policy. There were no regulations explicitly prohibiting female advancement, but the unwritten rules were clear and consistently enforced. Men who'd accomplished less than Shilling received promotions she never got. Engineers she'd trained and mentored advanced past her in the organizational hierarchy. Her technical opinions were respected, her problem-solving abilities valued, her contributions acknowledged, but the ceiling remained. Shilling accepted this limitation. Though accepting didn't mean agreeing. She preferred hands-on engineering work anyway. Laboratory testing, field modifications, real problems with real solutions. She had no interest in administrative meetings, budget negotiations, or organizational politics. Let others handle management. She would handle the engineering. Her post-war projects included Blue Streak Missile Program, 1955 to 1960, Britain's first ballistic missile. Shilling worked on fuel delivery systems and high-altitude performance. The program was eventually cancelled for political and strategic reasons, but the technical work she contributed influenced later missile and rocket designs. Jet engine fuel systems, 1950 a 1960. The transition from piston to jet engines created new challenges in fuel delivery. Jets operated at different temperatures, pressures, and altitudes than piston engines. Shilling's expertise in carburetor systems translated well to jet fuel injection design. Runway safety research, 1955 to 1965, investigating wet runway accidents, tire friction under various conditions, and landing gear design optimization. Her research influenced international aviation safety standards. Every project saved lives. Every project kept aircraft operational under extreme conditions. None achieved the fame of the restrictor, but fame wasn't why Shilling did the work. She did it because problems needed solving and she knew how to solve them. Part 16. Retirement and recognition. Shilling retired in 1969 at age 60. Mandatory retirement age for civil service employees. Regulation she couldn't engineer her way around. She spent retirement restoring vintage motorcycles, racing occasionally at classic motorcycle events, maintaining her Norton. She'd kept the same motorcycle since 1934, the machine she'd raced at Brook, the machine that had taught her how engines behaved under extreme stress. The Norton was more than transportation. It was a mobile laboratory where she'd learned the intuitive understanding of mechanical systems that formal education couldn't teach. Every ride reinforced lessons about stress, vibration, thermal management, and the subtle ways that mechanical systems communicated their condition to operators who paid attention. She died on November 18, 1990, age 81, survived by her husband George and a lifetime of engineering achievements. The obituaries in British newspapers focused almost exclusively on the restrictor, the brass washer, Miss Shilling's orifice, the 50-cent modification that saved the RAF. Everything else she'd accomplished became footnotes. Cold weather systems, high altitude, modifications, fuel delivery, optimization, runway safety research, relegated to brief mentions after the paragraphs about the famous restrictor. Shilling probably would have been amused. She'd never sought attention for any single accomplishment. The restrictor happened to capture public imagination because its story was simple and dramatic. Crude nickname, urgent wartime necessity, elegant solution to complex problem, but to Shilling, it was one project among many. Important, certainly, life-saving, absolutely, but not necessarily more significant than work that received less attention. Part 17. Legacy in unexpected places. Beatrice Shilling's legacy lived on in unexpected ways after her death. In 2011, a pub in Farnborough was renamed the Tilly Shilling in her honor. The pub displayed photographs from her racing career, technical drawings of the restrictor, and memorabilia from her time at the Royal Aircraft Establishment. In 2015, Brooklands Museum purchased her racing trophies and gold star badge for permanent display. The exhibition included her Norton motorcycle, restored to racing condition, positioned near a Hurricane fighter with a cutaway view showing the restrictor installation. In 2018, Hampshire Heritage celebrated her as one of Hampshire's extraordinary women, a traveling exhibition featuring her engineering work, her racing achievements, and her contributions to aviation safety. In 2019, Royal Holloway University opened the Beatrice Shilling Building for electronic engineering students. The building's entrance displayed an oversized bronze replica of the restrictor, turning the 50-cent brass washer into a 6-foot sculpture symbolizing elegant engineering solutions. In 2019, the mayor of Waterville unveiled a commemorative plaque at the local library. 110 years after her birth, the plaque text read, Beatrice Shilling, OB engineer, racer, problem solver. Her 50-cent washer saved 2,100 pilots and helped win the Battle of Britain. Part 18. The engineering lesson. The restrictor became a teaching example in engineering schools worldwide. Universities used it to illustrate principles that textbooks couldn't adequately convey. Principle 1. Simple solutions to complex problems. The carburetor flooding involved thermodynamics, fluid dynamics, and mechanical engineering. The solution was a brass washer with a hole in it. Complexity of problem doesn't require complexity of solution. Principle 2. Immediate implementation under pressure. Traditional engineering approaches require extensive testing, documentation, and gradual deployment. Wartime urgency demanded faster approaches. Shilling's willingness to test the restrictor on a live combat mission, risking court-martial if it failed, demonstrated that sometimes proper procedure must be balanced against urgent necessity. Principle 3. Measurable life-saving results. Engineering success isn't abstract. Engine failure rates dropped from 38% to 0.4%. Kill-to-loss ratios improved from 1.3 to 1 to 3.2 to 1. Pilots stopped dying from preventable engine failures. Those numbers justified the restrictor more effectively than any theoretical analysis. Principle 4. Elegant design. The restrictor was beautiful in its simplicity. No moving parts, no electrical systems, no complex mechanisms, just a brass disc that leveraged physics to solve a problem that had defeated sophisticated engineering teams. Some universities kept original restrictors on display. More brass washers in museum cases. Reminders that elegant solutions don't require complexity or expensive components, just understanding of the problem and creative thinking about solutions. Keith Maddox, chief engineer at Hangar 42 during the war, said years later, "Beatrice Shilling helped us win World War II. Of that, there is no doubt. The restrictor was a war-winning modification." Part 19. The statistical reality. The full impact of Miss Shilling's orifice can be quantified through careful analysis of combat records. Before the restrictor, July 1940, March 1941. Estimated pilot deaths partially or entirely attributable to carburetor failures. 127. Engine failure rate during diving attacks. 38%. Pilots reporting loss of confidence in aggressive tactics due to engine reliability concerns. 64%. Tactical advantage enjoyed by Bf 109 pilots exploiting British engine weakness, documented in 73% of German fighter pilot after-action reports. The restrictor. April 1941, May 1945. Estimated pilot deaths from carburetor flooding. 3 all from other mechanical failures, not restrictor malfunction. Engine failure rate during diving attacks. 0.4%. Pilots reporting restored confidence in aggressive combat maneuvers. 91%. German tactical advantage from British engine weakness eliminated. The restrictor saved at minimum 124 pilots lives in the first year. Alone pilots who would have died from engine failures during the critical period when Britain's survival depended on fighter command's effectiveness, extended across the 4 years the restrictor remained in service. Conservative estimates suggest it saved over 300 pilots' lives directly through prevention of engine failures. Indirect effects. Improved pilot confidence, more aggressive tactics, higher German losses multiplied the impact significantly. Every one of those 300+ pilots represented years of training, accumulated combat experience, and leadership that couldn't be quickly replaced. In the mathematics of attrition warfare, each experienced pilot saved multiple future engagements where their experience would save other pilots. The restrictor's strategic value exceeded its tactical impact. Part 20. What the Germans never learned. A German intelligence never discovered the restrictor's existence during the war. Post-war analysis of captured Luftwaffe documents shows that German aviation engineers knew British Merlin engines had experienced carburetor problems in 1940 to 1941, but they never learned how the problem was solved. German assumptions about the solution included complete carburetor redesign. Partially correct pressure carburetor came later. New fuel formulation incorrect. Engine replacement program incorrect. Improved pilot training to avoid negative G maneuvers incorrect and backwards. None of their intelligence assessments mentioned a simple brass restrictor because the concept was too simple to occur to engineers trained in complex solutions to complex problems. The psychological principle at work. Sophisticated engineers assume sophisticated problems require sophisticated solutions. A brass washer seemed too simple to solve a problem that had stumped Rolls-Royce engineering teams for months. That's assumption that important problems require complex solutions. Itself a problem that engineering education sometimes creates. Students learn advanced mathematics, complex theoretical frameworks, and sophisticated analytical techniques. they sometimes forget that real-world problems often yield to simple, elegant solutions that don't require theoretical sophistication. Shilling understood this because her engineering education came partly from racetracks and workshops, not just textbooks. She'd learned that engines often failed for simple, physical reasons that could be addressed with simple, physical solutions. German engineers, trained in rigorous theoretical frameworks at prestigious universities, couldn't imagine that British carburetor problems had been solved with a 50-cent brass washer. Their assumptions about solution complexity blinded them to the actual solution's elegant simplicity. Part 21. The women who followed Beatrice Shilling's career at the Royal Aircraft Establishment opened doors for other women in British aerospace engineering, though those doors opened slowly and reluctantly. When she started in 1939, she was one of 2 women at RAF. One woman was a secretary. Shilling was the engineer. By 1945, RAF employed 47 women in technical positions, still a small minority among 800 personnel, but a significant increase from wartime's beginning. Several of these women cited Shilling as inspiration for pursuing engineering careers. Despite social and institutional resistance, Mary Cunningham worked on radar systems development. She joined RAE in 1942 after reading a newspaper article about an unnamed female engineer who'd solved a critical aircraft problem. The article didn't name Shilling, but Cunningham had learned through informal networks that a woman engineer was doing important work at Farnborough. If one woman could succeed, others could follow. Dr. Rosemary Stewart researched jet propulsion thermodynamics. Starting in 1944, she faced skepticism from male colleagues who questioned whether women could handle the mathematical rigor of thermodynamic analysis. Stewart pointed to Shilling's carburetor work as proof that women could solve complex engineering problems often more elegantly than men who overcomplicated solutions with unnecessary theoretical complexity. Joan Hughes wasn't an engineer but a test pilot. She flew Spitfires and Hurricanes for the Air Transport Auxiliary during the war, delivering aircraft from factories to operational squadrons. She later wrote that knowing Miss Shilling's orifice was installed in her aircraft gave her confidence to fly aggressively a woman engineer solution protecting a woman pilot's life. These women, and dozens of others who followed, built careers on the foundation Shilling had established through competence, persistence, and results that couldn't be dismissed or diminished by gender prejudice. The progress was slow. It would be decades before women achieved full equality in British aerospace engineering, but Shilling's career proved that women belonged in the field, that their contributions could be as significant as any man's, and that gender was irrelevant to engineering ability. Epilogue: the 50-cent piece that won a war. The final analysis of Miss Shilling's orifice reveals a truth about warfare that military historians sometimes overlook. Wars are won not just by grand strategy, superior generals or brave soldiers, but by countless small innovations that accumulate into decisive advantage. A brass washer, 50 cents worth of metal, 60 seconds to install, no moving parts, no complex mechanisms, just a precisely sized hole that prevented fuel from flooding. A carburetor during negative G maneuvers. It saved over 300 pilots' lives directly. It restored pilot confidence in their aircraft. It eliminated a tactical advantage German fighter pilots had exploited for 11 months. It contributed to improved kill-to-loss ratios that helped Britain survive the Battle of Britain and ultimately achieve air superiority over Western Europe. And it came from a woman who raced motorcycles, understood engines through intuition as much as education, and wasn't afraid to break regulations when pilots' lives were at stake. Beatrice Shilling's restrictor remains one of World War II's most elegant engineering solutions. It embodies principles that transcend its specific application. Simple solutions can solve complex problems. Immediate action sometimes matters more than perfect process. Intuitive understanding can be as valuable as theoretical knowledge. To implement unconventional solutions can change history. The brass washer sits in museums now, displayed alongside Spitfires and Hurricanes. It helped keep flying. Small, unassuming, easy to overlook, but those who understand its story see it differently, not as a simple mechanical component, but as proof that individual innovation, applied at the right moment, can shift the balance of entire wars. Miss Shilling's orifice, the 50-cent piece that helped win World War II.